Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin and I'll be running through part 1 of problem set 20, intermolecular forces. Okay, number 1 says, why do real gases behave non-ideally at very low temperatures and very high pressures? Well, let's think about what ideal and non-ideally means first. One of the assumptions of the ideal gas law is that gases do not interact with each other. Okay, they don't interact. And if they did interact, then that breaks one of the assumptions of the ideal gas law, rendering it non-ideal, okay, making the gas a non-ideal gas. And so now it's asking, why don't gases that are at very low temperatures and very high pressures behave non-ideally? Or why do they behave non-ideally? It's because they do interact at very low temperatures and very high pressures. And why is that? Well, the reason is if you can think of low temperature, right? Low temperature means that molecules are moving less quickly. So if I have a high temperature situation here, okay, and then a lows here, it would look more like this, moving really fast here, moving really fast this way, and they're moving every which direction, right? Okay, but if I'm in low temperature conditions, they're moving a lot less slowly, right? And then they're kind of moving this way a little bit, moving a little bit this way, moving a little bit this way. And you can kind of see that the less that they move, the more likely they are to interact with each other, the more like or close they'll be to one another. When they're moving really fast, it's hard for them to catch, a grip with somebody or, catch an attraction with somebody. But when they're slow, okay, at low temperatures, this is low temperatures and high temperatures, they're going to interact a lot more. And the same goes for high pressures, same principle behind high pressure. High pressure is going to squish all the molecules together, right? If we have, even if they're moving really fast, what's most important is how close they are to each other. So if you compress the volume at which they're moving, or in the container which they're in, they're going to be in a very high pressure. And that means they'll be interacting with each other more. And so what comes into play are what we call intermolecular forces, okay? Intermolecular forces. Inter meaning between, molecular meaning molecules, and then forces like attractions or repulsions, okay? So it's really just forces between molecules. Previously, we've been talking about intramolecular forces, which are bonding, right? This is bonding, like ionic or covalent, right? But here we're talking about intermolecular forces, not intra. Okay, and there are 6 main intermolecular forces that you should know and be familiar with, okay? And I've tried to write them down in a composite graph here, or a chart, just to kind of consolidate everything into one thing, okay? So the very first thing that you should know is that London dispersion forces are in every molecule, okay? The reason is London dispersion forces is all they are is shifts of of electron clouds around molecules to create temporary dipoles is what we call them. Really quick, if you remember, water is a type of polar molecule, and the reason is because it has a dipole moment. A dipole moment is where one end of a bond is more electronegative or has more electron density around it than the other. Okay, and so it creates what we call a polarity. Now, in every molecule, it may not have this difference in electronegativity, but it will always have electron clouds. So let me give an example. Let's say I have this molecule, and let's say they're both nonpolar. So they don't have any dipoles, but remember, this cloud is made up of electrons, so this is all minuses on the outside, and they're just all they are is offset by the protons that are in the center. So that's why it's technically nonpolar, right? And then I've got another one here, here, and here, and here, all on the outside of this guy. Now, if I bring this close to the other molecule, right, like repels like, so a negative is going to repel another negative. So if they come together, this is what they would look like. At least one of them would look like this, okay, normal. But then the other one would look like kind of like this, okay, where the electrons have shifted back. Okay, now you've got a delta minus where you have extra negative charge and a delta positive on this side. And remember, we have still negatives on these on the outside of this electron cloud. Okay, and so this is the basis. This is actually the basis of all intermolecular forces, but this is the most basic form of it. This is the London dispersion force, or van der Waals forces, that you're going to find in every molecule because all molecules have electron clouds around them, okay? Just remember, the London dispersion forces have to do with these temporary dipoles that are created when electron clouds come close to one another, but that they are present in all molecules. And sometimes people will say that, oh, this is only for nonpolar molecules, which is true. It is for nonpolar molecules, but it's also for polar molecules. It's also for ionic compounds. Okay, it's in everything. Okay, everything has London dispersion forces. Okay, number 2, dipole-induced dipole. Okay, this is between a polar molecule and a nonpolar molecule. Same idea here. Okay, if I have a polar molecule, let's say here's we'll say this is my nonpolar molecule, and then I've got one that looks like this. It's going to be a dinuclear, and it'll look like this. Whoops, kind of like this, where the electron density has shifted towards one way. So I got a delta negative and a delta positive on this side. Okay, and then this is, remember, this is just nonpolar, so there's no dipole moment. But that means this has an extra negative charge, right? An extra negative charge, and this has less negative charge than normal, this side right here. So then you can imagine the same thing when this comes close to here, okay, they're going to start interacting with each other in the same way here by creating an induced dipole in this nonpolar molecule, right? So if I bring it close, then this is what happens. The polar molecule will likely stay the same. It'll have, this its end here still with the delta minus and the delta positive, but this electron cloud now shifts backwards like this, okay, and then I get extra negative charge over here because they repelled. So I got a delta minus right here, and then a delta positive, and then this is the interaction that happens, this delta minus with a delta positive, okay? That was what happened here. We had this delta positive and negative right here, okay? That's it's always positives and negatives that will interact to create these IM forces, these intermolecular forces, okay? So dipole-induced dipole, you have to have a polar and a nonpolar molecule, so you have to have two different types of substances to create this type of intermolecular force. Now, I've drawn these in order of increasing intermolecular force downward, okay? So right now we're on the second strongest intermolecular force possible. This dipole-induced dipole, it's strong, it's relatively strong, but it's not nearly as strong as some of the other ones that we're going to cover here in a second. Okay, number 3 says dipole-dipole, okay? That means we're dealing with two compounds that are both polar, okay, with the same principles. We're just going to briefly cover the rest of these, and we'll actually go through more in depth on the rest of them in the problems that follow. Okay, hydrogen bonding is a very specific type of intermolecular force. It's actually a dipole-dipole on steroids. Okay, I'm just going to put dip on steroids. Okay, on steroids, because all it is, it's the same interaction, but the only thing that differs it from it is that hydrogen has to be bound to an N or F, and then be interacting with another N or F in another molecule. Okay, and the reason that this is a dipole-dipole on steroids is because when N, O, or F are bound to hydrogen, okay, there's a very strong electronegative difference. If you remember electronegativity, that has to do with how much pull one element feels towards pulling electron density towards itself. Okay, and all of these molecules right here, the N or F, are super electronegative elements. And so they actually have an extra pull of electron density towards themselves, such that they create a gigantic dipole-dipole, okay? So actually water has very strong hydrogen bonding within its intermolecular forces, because it's bound to an oxygen, and then this hydrogen is bound to an oxygen, and then it's interacting with another oxygen on another water, okay? So that is the basis of hydrogen bonding. And those will be extremely important, not just for this class, but once you do, you get into like microbiology and stuff where you're working with DNA, that stuff has a lot to do with hydrogen bonding. So understanding these principles, especially hydrogen bonding, is going to help a lot. And then we'll just briefly cover 5 and 6 here. Ion dipole is just between an ionic compound and polar compound. So that's like if I dissolved table salt in water, that would be 8 Na plus and Cl minus, just roaming in water. Okay, if I have just a bunch of waters, I'll just put little circles for the O's and H's, okay? That would be a polar ionic compound, water being the polar substance, and then the NaCl being the ionic substance. And then ionic is just between two ions, really. That would be like between Na and Cl, okay? So that's it. That's really the breakdown of all the intermolecular forces that you should know, and the types of molecules that make up those intermolecular forces. All right, number 2 says acetone, or 2-propanone, is the primary component in most nail polish removers. It is miscible or completely soluble in any proportion in water due to hydrogen bonding. Here we see that principle again. Draw the hydrogen bond between acetone and water, and put the box around the 3 atoms that are important for the hydrogen bond. Okay, so I'm going to draw it down here, okay? Let's draw acetone first. Acetone, I'm going to use organic structures here. So if you don't know what this looks like, or if you don't understand what this means, I'll just know that every bend and end here, every bend and end is a carbon. So this would be a carbon, carbon, carbon. And then wherever there's nothing else bound, you always assume hydrogens are bound to saturate the carbon. So here we'd have 3 hydrogens, hydrogens, and hydrogens there and there. Okay, so this used to be part of the Chem 105 curriculum, but it's been since taken out. So I would have just looked this up if I were you. Okay, all right. So this is the acetone molecule, and we're going to look at how it interacts with a water molecule, which hopefully you do know the structure of, and it looks like this. Okay, and there's a bend in it. And so the interaction here is, remember, it's got hydrogen has to be bound to an N or F, and then interacting with another oxygen that's bound, or that doesn't necessarily have to be bound to an N or to a hydrogen, as long as the hydrogen itself is bound to another oxygen. Okay, so this here, the box area that they wanted you to put in here, that's going to be the 3 molecules important for this hydrogen bond. So you've got the hydrogen, and then it's bound to an oxygen, and then it's binding to another oxygen. Okay, so that is a hydrogen bond. And remember, this could have been an N, a nitrogen, or a fluorine here or whatever. Okay, and that would still work as hydrogen bonding. All right. Okay, number 3 says, which of the following will exhibit the strongest London dispersion forces, and explain your reasoning. Okay, so you'll notice with all of these, the very first thing you should do in every question that they ask you is determine the intermolecular force at play. Okay, the strongest intermolecular force at play. Now, by the strongest, I mean how far down this list can you go? Okay, meaning, which is the dominant intermolecular force is what we're going to call it later. Okay, dominant. Okay, so number 3, on 3A, helium is a noble gas. Okay, and noble gases only have London dispersion. So I'm going to put London dispersion there. Nitrogen is a diatomic molecule that looks like this. It's perfectly straight and perfectly symmetrical. And this bond, these have the same electronegativity, so this is going to be perfectly nonpolar, which would make only London dispersion forces the only possible forces there. And you'll notice that that's going to be the same for all of them. So that means the only thing that differs between them is their size. Okay, so the very first thing you should do is look for the most dominant intermolecular force. Now, if they're all the same, okay, the next thing you need to do is look at their size. Now, helium obviously is super small, right? So I'm going to put this as, I'm going to label 1 through 5 in terms of smallest to largest. Okay, so helium is obviously the smallest. Okay, and then if you look on the periodic table, based on periodic trends, you should notice that it's fluorine, and then it's oxygen, and then nitrogen, and then iodine. Okay, that would be the order in increasing size based on where they are in the periodic table. Remember, size increases to the left and down. Okay, size increases to the left and down on the periodic table. Okay, so that means iodine is the biggest. Now, that is going to have the biggest effect on which one has the strongest London dispersion forces. But in this case, the reason that iodine is going to have the largest London dispersion forces is because of its size. The bigger it is, the more manipulatable its electron cloud is. Okay, so remember back when we talked about what's called the Z effective, or effective nuclear charge. That has to do with the interaction between the nuclei and the outermost valence electrons. Now, if you can imagine, if it's further away, right? Let's compare this to, let's say, nitrogen, right? The nitrogen to nitrogen electron cloud is probably something like that. Okay, now if I draw the nuclei here, okay, and then I draw, an electron here, an electron here, an electron here. The distance between these guys is a lot smaller than the distance between these guys. So just by distance sake, the interaction, or the strength of the interaction between the nuclei and the valence electrons is a lot weaker in iodine than it is in nitrogen. Okay, which means it's easier to move this electron when it's hit with another electron, meaning when another electron, let's say from another electron cloud, comes to repel it, it's a lot easier to push it because it doesn't have this lock on super hard, whereas the ones on nitrogen do. Okay, so what that does is, remember this principle here of electron clouds coming together and then repelling one another and creating temporary dipoles. The same idea here, when another iodine molecule, okay, comes in contact with another iodine molecule, it's a lot easier for this cloud to repel this other guy's cloud backwards, and then create that temporary dipole interaction. Okay, it looks like this. Get a delta positive here and a delta negative here. The delta here is just it just means partial. Okay, the lowercase delta just means partial. And then here I've got my iodine and my iodine, and then I've got my electron cloud here that's interacting with that delta positive now that it just created by repelling the other guy's cloud. And so the smaller you get, the harder it is to manipulate that cloud. And we call this polarizability. Okay, polarizability. Now, this polarizability concept is really important in every intermolecular force that you'll deal with because, especially in London dispersion, because it has to do with how well does the electron cloud get shifted. And if it shifts well, then the interaction is a lot more favorable. It's going to be a lot stronger. And you'll notice that as you go down this list of intermolecular forces. Okay, so that's the basis of how you want to think about not just London dispersion forces, but intermolecular forces in general in terms of size and electron clouds. All right, number 4. Number 4 says state the dominant intermolecular force, meaning the most overwhelming intermolecular force that causes most of its behavior. Okay, so when we're doing that, what we're really looking at is this list here. Okay, this list is going to tell us what in order of increasing intermolecular forces that there are. So if I find that there's a dipole, if it's a polar molecule, then and there's nothing else further down, then it's going to be dipole. Even though there are London dispersion forces there, I'm only going to list dipole because that is the dominant intermolecular force. So what you have to do, you kind of have to go back a little bit in the material and make sure you remember structures and angles and dipole moments and electronegativity differences to be able to do this. Okay, so you're going to have to be able to determine whether these are polar or nonpolar or ionic, and that will determine largely what the intermolecular forces are. So letter A says beryllium hydride. Okay, so that means beryllium is here. Now if you look on the periodic table, beryllium is in the second group on the periodic table. So it's got 2 valence electrons around it. And it's actually okay with just having the 2 hydrogens here. Okay, so it actually ends up just making a bond here and here. And even though it doesn't fulfill the octet rule, it actually this is one of the few that breaks the octet rule. In fact, it's fine if you look at especially because if you look at the formal charge on everything here is 0. So it actually ends up being super stable. So now, given that this is my Lewis structure, okay, I would expect this shape to be linear because I don't see any lone pairs, and it's going to be so it's going to be in a 180-degree fashion because my steric number is 2, okay, and I have no lone pairs. So even if there were dipole moments here, they would be canceled out. So I'm not even going to look at that because this is a straight line. So I know that for sure this is nonpolar, which means the only possible intermolecular force that beryllium hydride experiences between other beryllium hydrides is London dispersion. Okay, that's the other thing is they're expecting you to state the dominant intermolecular force of this guy between other water molecules, okay? Not between, no, so we're not going to be dealing with dipole-induced dipole, I should say, or ion dipole, because those require substances of 2 different identities, okay? So in this case, we're only going to be dealing with the molecule itself interacting with other versions of itself. So I'm going to put London dispersion, and it can't go further down because all it is nonpolar. All the other intermolecular forces require some sort of dipole moment, okay? And this one does not have one. All right, letter B. This is water, obviously. So let's look at water really quick. So we have this bend in it. So I know that there's going to be, if there's dipole moments in these bonds, then it's going to not be canceled out because there's a bend. And so it becomes asymmetrical. And there is an overall dipole moment, but it also satisfies the criteria for being a hydrogen bond, right? If this is interacting with another water molecule, then I've got this hydrogen bond going on right here. But, so ultimately, I could list both London dispersion, dipole, and hydrogen bonding as possible intermolecular forces that water experiences, right? These are all possible intermolecular forces, but the dominant intermolecular force here is the hydrogen bond because it is the strongest. So I'm going to put hydrogen bond. Okay, hydrogen bond. All right, XEF2. Hopefully you're able to draw the Lewis structure for something like this, okay? We got xenon in the middle, and then we've got F, and then F, and then all these electrons around it, and then we've got these 3 lone pairs on the middle one. Okay, so if you don't know how to do that, I would go back and review Lewis structures, okay, drawing Lewis structures. I'm not going to cover that a ton here because that would take up too much time away from this concept. Okay, so now if I look at this, I've got 3 lone pairs, okay, but the steric number is 5, and if I have 3 lone pairs, that actually becomes linear. This is a weird case of a linear version of a molecule that has lone pairs on it. And so this is actually 180 degrees here between the two bonds. And so I know even if there are dipoles, which there are, by the way, because fluorine is one of the most electronegative elements on the periodic table, that they're going to cancel out. Okay, so this becomes nonpolar, which means the only possible intermolecular force that there is London dispersion. Okay. All right, letter D says pH 3. Okay, so that's called phosphine. Okay, it looks a little bit like ammonia, but it's just phosphorus. Okay. And if you do the correct Lewis structure, it looks like this. Now, you may be tempted that because ammonia looks like that this might be some sort of London or some sort of hydrogen bonding. But remember that hydrogen bonding only occurs between N or F, and this is not an N or F molecule. Additionally, if you look at the electronegativity differences between hydrogen and phosphorus, you'll find that the difference in electronegativity is less than 0.5, okay? Now, when it's less than 0.5, if you remember, that becomes a nonpolar bond, okay? So this bond doesn't have a dipole in it, okay? There's no dipole moment going on, which means even though this is asymmetrical, you're going to find that this is a nonpolar molecule. Okay, so this overall molecule is nonpolar because there's no dipole moment in it. So that becomes London dispersion as the only possible dominant intermolecular force in nonpolar compounds, okay? All right, letter E says chromium chloride. Okay, now this is a transition D, a transition metal in the D block. Okay, so you have to look at chromium. Where's chromium on the periodic table? Well, it actually doesn't matter because as long as you know chlorine's -1 charge, it'll actually tell you the charge on the chromium. Okay, and the chromium is 3+. Okay, 3+, and that means they just switch this here to make it into this. Now, how did I know that it was going to be a negative and a positive here? Well, if chlorine is not interacting, chlorine is a nonmetal, right? And nonmetals, if they bind with another metal, okay, like chromium, that becomes an ionic bond. Okay. Remember, nonmetals to nonmetals, is a covalent bond. Okay, metallic a metal to metal is called metallic bond, and then an ionic bond is a nonmetal to a metal, and that is an ionic bond. Okay, so that's how I knew this is an ionic bond because chromium, a metal, is interacting with a chlorine, a nonmetal. So we have to kind of go back in our minds a little bit to what kind of the intramolecular forces are, or the bonding, and then determine what kind of intermolecular forces they'll experience between the molecules. So that means this chromium chloride here, this chromium 3 chloride, right, is going to be an ionic bond because it's a nonmetal and a metal. And so this chromium chloride would interact with other chromium chlorides because this chromium, even though it's 3+, and it's sitting next to Cl minuses around. And then those Cl minuses can interact with another Cr3+ here, which is interacting with other Cl minuses over here. Okay, so this right here is technically an intermolecular force because this is technically an intermolecular molecular unit, and this is a molecular unit, and they're interacting with one another. So this is ionic. Okay, ionic. All right, SF2. Let's look at SF2. So SF2, if you do it correctly, should look like this. Okay. So there's a bend in the molecule, and I've got dipole moments in these bonds if you look at the electronegativity differences. And honestly, anything bound to fluorine is going to have a dipole moment. But whether the molecule does or not is going to be determined by the shape. And it looks like the shape is bent, which means there's an overall dipole downward, right? And that makes this polar, so there's dipole forces in this, okay? And that would be the strongest type of intermolecular force that there is. All right, last one. This is carbon sulfide here, carbon sulfide. Now, if I look at carbon, that's a nonmetal. With sulfur, that's another nonmetal. So I'm going to expect this to be a covalent bond. So I got 4 electrons around carbon, and I've got 2 lone pairs and then 2 bonds around the sulfur. So I'm going to expect the 2 sulfurs to make 2 double bonds with this carbon. So it's going to be sulfur here and then there. Oops, sorry, put too many lone pairs there. Okay, so it should look like that. Now, even if there were dipoles in here, I don't even need to look because they're going to cancel out. Doesn't matter, okay? And that would make this overall nonpolar molecule, which makes this a London dispersion as the dominant intermolecular force. Okay, so honestly, I realized that I've gone over some material, or I've used some previous material that maybe some people didn't have a great grasp on. And you'll notice that a lot of Chem 105 stuff builds off itself. So if you don't understand Lewis structures or VSCPR, which is the model I was using to create these shapes or determine the dipole moments with electronegativities, okay, I would go back and review those because those are going to be critical for understanding intermolecular forces. That's going to finish it up for part one of intermolecular forces. We'll see you in part two.